All right, we're going to do a little bit of modeling motion here. And what I want to do is go back to the idea of a horizontal spring. If I stretch it from this point here and let it go, maximum kinetic energy at the equilibrium point, maximum potential energy as it compresses, it's going to shoot it back the other way, maximum kinetic energy here as well, maximum potential energy here. And what we have is that based on conservation of energy, however far I extend it, that should be how far it gets compressed. That should make sense. Now, what we're going to refer to this is the amplitude. This is going to be the amplitude of our oscillation. How far away from equilibrium does this thing stray? You see me write A there? Nice, yeah. And so what we find is that it goes this far away, and then when it compresses, it goes this far away from equilibrium. And so it's oscillating between those two extremes there. And what I want to kind of diagram out for you is what this is going to look like. You know, you actually have a lot of things happening in between, right? It's gaining speed here as it moves to the left. And what it's doing is it's losing speed here as it moves to the left over here. It's gaining speed as it moves to right here. And it's losing speed as it moves to right here. And then if we're kind of keeping track of the position, I'm just going to draw that because that is going to be the model for our motion here. And if we take a look at that, you know, this thing is changing amplitude as a function of time, essentially, or changing position as a function of time. And we have a maximum amplitude there. We can model the position function as a function of time. X as a function of time is going to be equal to A times cosine 2 pi ft. And one thing I want to point out to you here is this. This function right here is in a radian mode. That's the way it's set up. If we wanted to model this function in degree mode, that number would have to be different. We're going to leave it the way it is because radians is the golden standard here. And then what we have here is we've got a function that basically oscillates between 1 and -1. But then if we multiply that function by a, it oscillates between a and -a. So what's going to end up happening is that if I'm looking at my function as a, my position as a function of time, this gets it to me. Frequency is measured in hertz. Time is our variable here. So you have x and t changing. If we were to graph that, something you guys should have done in pre-calc, x is a function of t. If I graph out one full oscillation, it's entirely possible I screw this up, but let's hope I don't. There's our cosine curve. What we have here is that this value right here is a, and this value right here is -a. So there's our cosine curve as a function of time. And why don't we write the function again just so that it can always be in front of us. X is equal to A, which is the maximum amplitude, how far we stretch it away from equilibrium, times cosine times 2 pi ft. And so what we have just diagrammed out is one full period. So that means that this point right here is capital T. That's the period there. Now, going back to the motion here, the speed of this thing is changing all along the way. It's shrinking, it's growing, it's shrinking, it's growing. That is actually going to be a sinusoidal function as well. Maybe I bring back the picture here and take a look at the speeds. You know, at the beginning, the velocity here is 0. The velocity here, it's at its maximum value and it's to the left, so it's got to be some sort of negative number. The velocity here is 0. Velocity here is its max here, but it's moving to the right, so it's got to be some sort of positive number, and the velocity is 0 here. Let's take a look at what that's going to yield here. It's actually going to yield us another sinusoidal function, v as a function of t. Let's take a look at what's going to look like. All right, so we started out with a velocity of 0, we go negative, and then we'll hit 0 again. So we're here, we're at our most negative value, right about there. We're at 0 again here. That's right there. Now we're going to be at our maximum value, which is most positive. And this should be equally as large. These 2 points have the same speed right here. And then we're going to hit 0 again at the very end. So taking a look at that curve, I've graphed out how the velocity changes during one full oscillation, and that looks like that. Now that's a sinusoidal curve, and it's actually a negative sine curve. And if we want to model this behavior, the velocity as a function of time is equal to 2 pi f times a, negative 2 pi f times a. There's a negative sign right there. And then it's going to be sine 2 pi ft. So there's our function. And one thing we want to point out too is that if you cover this, we've got a sine function there. That function oscillates between +1 and -1. If you want to know what your max speed is, well, the maximum value of sine is 1. So your max speed here is going to be equal to plus or minus 2 pi f times a. Your maximum position here is equal to plus or minus a, because that function, its maximum and minimum values are 1 and -1. So that's actually a convenient way to get the maximum speed. You can always do it by conservation of energy like we've done in the past, but that gives you another way of doing it. So if you happen to know, I would say enough information to get the frequency of this spring here, for example, if you know K and M, then you can easily get Vmax really quickly just by calculating the frequency and then doing 2 pi Fa. What you might also notice is that obviously the max speed actually does depend upon A itself. So we saw that the period is not affected by the amplitude, but the max speed obviously is. All right, last thing we need to think about is acceleration. Acceleration is a function of the force that's acting on this object from the spring here. There's an elastic force there pointed to the left. There's no force there, it's at the equilibrium point. There's an elastic force there pointed to the right. So we got a negative force, we got a positive force. You go and have negative force here, no force there. And you know what? This is changing all along the way as well. It's a function of how far it's extended. It's a function of Hooke's law. So based on that, we can look at our acceleration as a function of time. And what we saw is that initially is pointed to left at its most negative value, right about there. And then once it hits the equilibrium point at 0, then once we hit the maximum compression, it's at its most positive value. Then it's at 0 again, and then it's at its most negative value. So most negative, 0, most positive, 0, most negative. And what we have here is a curve. And what you may have noticed is I've vertically stacked these curves to show you that we can have all these things on the exact same time scale. That's the period there. That's the period there. I've graphed out one full period for you. So essentially our acceleration, if you take a look, and you know what, my drawing is not the best drawing, but I was hoping it would look more like that. That's pretty crappy too. It's going to be a negative cosine curve. I'm going to give up with my drawings here. It's going to be negative 2 pi f a. Let's put the 2 pi f in parentheses and square it. And then it is going to be cosine. And what you're going to see is that the inside of the sinusoidal function is always the same thing, 2 pi f times time. Looking at that, what we have here is that your maximum acceleration would be plus or minus 2 pi f, square that, times a, where again a is your amplitude up here. And then we can model all three of these things with sinusoidal functions. So what ends up happening is that you actually do get some good applications for sinusoidal functions here. What we're going to find is that it really doesn't get brought up in this course as much, but pendulums can actually be modeled with the same exact equations. So if I'm looking at those equations here, what we did was we said A is how far we extended the spring. Well, if you think about a pendulum goes back and forth, and it's doing this. It's going over this distance and over this distance. So the two best ways I've seen them model these functions using a pendulum is for A to be a function of arc length as to how far away it is from this equilibrium point here. Maybe it's this far away, maybe it's this far away. Or the other thing is you can have A in degrees, or you could do radians as well. And then that would tell you, how far away it is in terms of degree spacing. And then the rest of the functions follow suit as well. So we can model simple harmonic motion with sinusoidal functions.